All right, so welcome in, everyone. My name is Brian. I'm the chair of the mathematics department here at Okanagan College. This morning, we are starting to look at modular arithmetic, specifically looking at addition, multiplication, and exponentiation to start off here. All right, let me get set up and ready to go. Yep, got it. I mean, one might argue that like a really good understanding of modular arithmetic and number theory is kind of the foundation for us for understanding cryptography. If you haven't used modular arithmetic before, essentially what we're going to be thinking about is remainders after doing division. So that's the key idea here. And once we start understanding some of the basic properties, some really interesting additional properties are going to pop out, specifically allowing us to identify classes or categories of objects that have similar properties. So that's kind of where we're after, or kind of where we're working towards by the end of the video series here. But let's start with a basic definition. So we're going to say that if a and b are integers, let's say that a is congruent to b modulo or mod n if the following is true. If n divides a minus b. And when we use this divide symbol, it means we want to divide evenly, effectively, right? So we want to have a zero remainder here. And using some mathematical notation, we might write this as a, for the purpose of our course, we'll use a triple equal sign here. So we'll show this will be kind of our congruence. So A is congruent to B mod n. This is typically how we would write that and read this. And in the next video, we'll talk a little bit about why we use the word congruent. That'll become a little bit more clear. But for now, just understand that's our terminology. That's how we're going to get things set up. So Zach is saying, had a teacher who called a minus b a multiple of n. Yeah, that's true. Instead of n divides a minus b. That works as well. So let's take a look at some first or preliminary examples. So let's take a look at 20 take away 2. So we know that 6 should divide 18. So 6 should divide 20 take away 2. So what does that mean for us? Well, since 6 is the number that's actually doing the action of dividing, that's typically our modulo base number. So here, 6 is dividing 18. So, or in other words, we can also think about 6 as dividing 20, and we're going to have a remainder of 2 after we do that division. So if we take the number 20 and we think about dividing it using the number 6, we're going to get 3 for 18, and then we're going to get that remainder of 2. So this is how the pieces get set up and into play for this particular relationship. So 20 here is kind of being divided by 6. When we do that, we get 18 as the largest number that can go into 20, and then we have this remainder that's left over that is 2. So let's do this one more time. These numbers that we have on the right-hand side of the division symbol, they don't have to be positive integers. They could be any kind of integers, to be fair. So, for example, I could say 9 divides 4, subtract negative 5. That's certainly true because 4 take away negative 5 is 9. So we know 9 does divide 9. So how do we set this up as a relationship using the mathematical structure we saw up above? Well, 9 is the number that's doing the dividing, right? So 9 is going to be kind of our modulo arithmetic number that we're working with. And what we're saying here is there's a relationship between 4 and negative 5 that we want to look at. If I start with 4, and I go through this process of dividing by 9, well, we do have 4 left over. But there's this interesting relationship here that says, okay, well, 4 and negative 5 must also somehow be connected in this modulo arithmetic universe. Hey, MathBond, how's it going? The UK has abandoned clocks in schools in favor of digital clocks. I don't know how I feel about that. All right, so let's go ahead and just get through a few more examples. Here we're going to fill in the blanks. Feel free to let me know how your days are going, guys. Mine's going pretty good so far. And I mean, to be honest, any day in which you can do number theory, that's a good day, right? Alrighty, so we have a couple of examples here with various blanks. So we have blanks on
chickens, optimization, maximize
of the values before the modulo we're working with.
Order,
we have
with weighted
blanks
edges.
on the left-hand
Cross
side
the
and
road,
blanks in the modulo.
minimize
So
path
a
length,
bit of a mix here.
Avoid noise. Zeta, cluculations, sine.
Cluculate. Oh my gosh. Okay, show. Thank you for that. So let's work with the first two. So here we're starting with a number 6. We're working in a modulo 4 environment. So we're really thinking to ourselves, 6 divided by 4. Right, so this is kind of my thinking process. I know that that's 1, and I know that there's going to be a remainder of 2 after I do that division. Hi, Obi. How's it going? Happy Thursday to you. So same thing down here. We kind of want to think. We start with 17. We're in a division by 11 kind of environment. When I do that division, I can only get 1 11 into 17. And then I'm going to be left with a remainder of 6. So yeah, Rex, you make a good point. There might be some other possibilities here, right? These are certainly not the only possibilities we could get, but they are possibilities. Because if we look at, say, this first one, just as kind of like a little aside here, all I really want to do is make sure that 4 divides 6 take away something. I just need to figure out what goes in that blank, right? Now, the easiest number we can pick here is 2. Rex had suggested maybe 10 would work. And I think that should work as well, right? If we go 6 subtract 10, that should give us -4, and 4 should divide -4 evenly. So 10 is another possibility. So 2 is just one of those possibilities. We're actually going to see that there's an infinite number of possibilities that would work. But good noticing there, Rex. Yeah, slim is true as well. If you want to be super lazy, just put the same number in, right? We know that 6 has to be congruent to itself, mod 4, because 4 is going to divide 6 minus 6. Right? 4 should divide 0. So every number is always congruent to itself in any modular base as well. I love how your troll actually turned into a real correct answer. I think that's awesome. 0 is a multiple of 4. Yes. Okay, what about something that's congruent to 4 mod 12? We could use Slim's idea and just put 4 in. We know that 4 should be congruent to itself. But could we find another number other than 4? Maybe something bigger than 4.
Iterate. What's the next problem? Feed me inputs. I'll output a zeta solution in O1. Sine, cosine.
Oh wow, Slim, you're stealing my thunder. But yeah, that is the reflexive property of an equivalence relation, which we will talk about a little bit later. So yeah, of course, we could put 4 here. And if we're in a division by 12 kind of environment, well, what we could do, or at least how I think about this sometimes, is I go, okay, well, if 4 is my remainder, and 12 is the thing that I'm dividing by, I can always make new congruent numbers by adding 12s. So, for example, I could pick, like, 16. 16, if I do division by 12, should give me a remainder of 4. And I could add whatever multiples of 12 I want, right? I could keep going and maybe add 24, so 28 would work too. Right, 28 divided by 12 is 2, that gives us 24, and then I'm going to have those 4 pieces that are remainder after doing that division. So that's one way I can tackle these kinds of problems. Okay, if I know what I'm dividing by, I can just keep on adding that kind of base number, that divisor, until I get to another number that's useful for me to use. What about this one? This one has a -1 in it, which I think is kind of weird. Well, I guess we could probably use the same strategy and see if it makes sense. What if I take -1 and I add 7 to it? That would give me 6. Do we agree that 6 is congruent to -1 mod 7? So in other words, if I look at the subtraction of these two elements, is it divisible by 7, right? That's the definition. So if I'm ever kind of wondering if it's true, we could take 6 subtract -1. We could convince ourselves, okay, yeah, that difference is 7, so these two things should be equivalent mod 7. So everything kind of checks out here. Now with the last two, the blank is actually in the base that we're working with, right? That divisor that we're working with. So is it possible for us to find a number such that if we start with the number 70, we're going to divide 70 by some number to get a remainder of 3. So we need to get up to like 67. Is that true? Right, so I kind of have to like take 70, I need to divide by something, and I need to get 67 with the remainder of 3. Right. I made these notes before 6-7 was a thing, Raven. I promise. I promise. I did not plan this. So yeah, I suppose one way to make this work is just to take 67 as the thing we're dividing by, right? And we could just put that in there. 67 goes into 70 once with a remainder of 3. That would work. Slim is asking a very good question, which is 67 prime? That might be important a little bit later, right? It's nice to have prime modulos, and we'll see why in a little bit. So 67 might work. Are there any other numbers that work? Is 67 prime? It feels like it's a prime number. We'd have to get... Oh, Floofy has verified 67 is prime. I was thinking to myself, you'd have to get a 27 in there, which would leave a 40, but then 40 is not divisible by 3, so you're going to run into some trouble. Yeah, so 67 feels like it probably should be prime. Ooh, this is interesting. Negative 52 congruent to 13 in some mod. So I need to... So the way that I want to think about this is I need to start with negative 52, and I need to add multiples of something, right? I need to add like k times a blank number, and I need to land on 13. So, I mean, we could pick the easiest number, which I suppose is just 52 and 13, right? We just need to span that distance. So 52 and 13 is 65. Uh, 65 is divisible by 5. Is it divisible by anything else? So could we use 13s or 5s would be my question. Right? Like, can I use mod 5 here? Right? Like, I think I can take negative 52 and I can add 13 groups of 5, and that would get me to 13. So actually, what I might do is I might pull up my calculator here too. Boop, boop. And so kind of using the idea that Slim was talking about, where, you know, maybe it's not going to be, in the future, it might not be helpful for us to choose 65, but it might be helpful for us to choose one of the prime components of 65. So this is all I'm looking at. I'm looking at 52. If I can keep adding 5, right? And eventually, by keeping adding 5, I will eventually land on 13. So that's one way to deal with this problem. Of course, the easiest way to deal with the problem is just to straight up add 65 right away, and boom, we're going to land at 13. So 65 is an answer to this problem. And then what was the other one? 13, I think, right, was the other prime factor. So we could keep adding multiples of 13 until we eventually get to 13. Oh, that's interesting. So 52 is 52 divisible by 13? Because I saw that we passed by 0 there. Yeah, okay. Oh yeah, that makes sense. 52 cards in a deck, there are 13 cards per suit, right? So yeah, 15 is divisible by 13 as well. I noticed that we passed by 0 on the way up, so I was like, oh, that's interesting. Okay, so 5, 65, 13 are all possibilities for that particular blank. So hopefully that gives you some insight into, if I'm working with some modular arithmetic and I'm trying to fill in some of these blanks, some strategies for how to fill in some of those blanks. And I think one of the most important things, and Zach had mentioned this earlier, is this idea of multiples of something is important, right? So we can think about A being congruent to B mod n as saying something like A is equal to B plus some multiple of that base that we're working with. And here K is just some integer. So there's like a very natural way to think about mod arithmetic as some kind of linear combination, right? And that's because of the we're effectively using the division theorem here, right? So there's a number that we're starting with. We have our divisor, we have our quotient, our remainder, etc. Right? So that's why it feels very natural here that there's a connection between these two things. So what we want to do next is, now that we have an idea of what these numbers mean and the interplay between these numbers, we want to start studying some of the operations and trying to develop some of the properties that some of the folks in chat already have alluded to a little bit. So typically in mathematics, we might say, okay, now that I have this new structure, this new thing, how does it work with the operation of addition? How does it work with the operation of subtraction, multiplication, division? So any kind of operation that we have for other sets of numbers, how do those translate, or how do they port over into the structure that we're trying to develop? So we want to study properties maybe for addition, subtraction, multiplication, division, I don't know, exponentiation, taking roots. Like, all of these seem like natural things to want to talk about because we're working with like integer numbers, and we know how to do this with integer numbers already, right? So maybe we can extend some of these properties, or maybe by extending some of this stuff, we'll find something that's really, really interesting. Hey, Hitch, how's it going? So addition and subtraction tend to go hand in hand, and some professors might even tell you that subtraction really doesn't exist. It's just addition of the inverse or something like that, right? It's just the additive inverse of the object or in the field that we're working with. Why is there a weird blinking thing here? Can you blink over here? So just for the sake of time, I'm just going to go ahead and summarize some of the really nice properties for addition using modular arithmetic. So let's say we have A is congruent to B mod n, and we know that C is congruent, that's too many things, C is congruent to D mod n. Then what do you think A plus C should be congruent to? So if you're kind of curious about properties like this and how this interplay works, you might start working on some small examples, right? So like take some numbers, I don't know, let's take like 2 is congruent to Actually, we need a bigger number. Let's take like 7 is congruent to 2 mod 5. And 9 is congruent to what mod 5? 4? So is it true that if I add these things up, 7 and 9 is 16, right? So I get 16. Is 16 congruent to, I don't know, maybe we're thinking that the remainders would get added together, 2 plus 4. Is that true? Is 16 congruent to 6 mod 5? That seems reasonable. I mean, we've only picked one particular example. It is true. But the beautiful thing about arranging things and then dividing by the same divisor is that if you arrange all of the remainder pieces and you still work with that same divisor, the eventual remainder is still going to come out the way that we expect it to. So yes, we can take these remainders, we can add them together, and then continue to divide by n in this case, and end up with a new congruence relationship. So that's property number 1. Right, so addition works really, really nicely. If I add on the left-hand side of the congruence, that means all I really need to do is consider an addition of the remainders on the right-hand side, and everything should be okay. Okay, property number 2. If I take a congruence relationship, so like A is congruent to B mod n, and I maybe add or subtract something from the left-hand side. So let's say I want to alter A by some value. How do we think that's going to affect the right-hand side, as long as I stay in the same mod base? Yeah, you got it, Rex. So, again, we can kind of take an example, like maybe we know 7 is congruent to 2 mod 5. And we could say, well, what if I want to increase this a little bit? Like maybe I want to take 7 and I want to add 10 to it. Right, so now maybe I'm curious about 17 mod 5 instead. Well, 17 is what? 2 mod 5, right? 17 is 2 mod 5. But wait a second. This should be... If we think that this is going to be B plus or minus C, shouldn't this be 12 mod 5? Floofly, you got it. You really added 0 mod 5, right? So yeah, we can scale both of these up to get... Basically, we're doing this. We're scaling both of them up to get 17 congruent to 12 mod 5, but 12 mod 5 is really just 2. So we're okay. And again, if you kind of think about it in terms of remainders, right? So if you're doing this division by 5 to get a remainder, it doesn't matter if you start with like the remainder or you start with that original number, right? As long as you're adding or subtracting the same amount of objects and then doing that division afterwards, you haven't really, like you've altered the remainders by the same amount, effectively, right? That's all we're saying here, right? Like if I take 7 objects, 1, 2, 3, 4, 5, 6, 7, or I take two objects, these two things are the same on division by 5, right? So division by 5 means I'm just going to start making groups of 5, and the remainders are the same. That's what we're saying here. If I add, I'm not going to add 10 because that's a lot of things to draw, but let's say we added 3 objects. I'm going to add 3 more objects. Maybe I'll do it in green so you can see it. I'm going to add 3 more objects. Boom, boom, boom. And 3 objects over here. Well, now over on the left-hand side, I now have a new group of 5. So my remainder, after thinking about division by 5, is 0. And over here, I also now have a group of 5. So it also has a remainder of 0 when dividing by 5. Right? So as long as we start with a relationship that says the remainders are the same, when I add the same number of objects to both of those pieces, when we go to do the regrouping happens in a very similar kind of way, right? That ensures that our remainders don't get arfed up effectively. So again, another really nice property, I can add or subtract any integer value from the left or right-hand side mod n, and we should end up with a similar congruence, right? Just because of this really nice property of working with remainders. I don't have page numbers on me. I wish I had page numbers. What page is this? Well, I don't think we need to do any of that. Okay, that's fine. So I'll just make a little note here that this is typically the strategy that we use when working with negative numbers in our modulo arithmetic setting. And we've used this already. That is, if I start with some kind of negative integer and I want to rewrite this, maybe let's say in mod 10, and I want this to be a positive integer, well, the idea here is just to let's add 10 to both sides, and then I get the thing that I want, right? So that's kind of the strategy here. I can always add, in this case, multiples of 10, and that's going to ensure that the remainders that we're working with are going to end up staying similar. So negative 7, if I add 10 to that, that tells me it should be congruent to 3 mod 10. So whenever you get negative numbers, you can always change them into positive integers using this kind of strategy. Hey, Drizzy, how's it going? So b plus c minus a plus c equals b minus a, which is divisible by n by assumption. Yeah, so Drizzy is giving us some insight into why the proof of this might work. So maybe it's worthwhile for us just to make a little caveat note here. Let's see if I can pick up what you're throwing down here. So b plus c subtract a minus c, right? So by definition, we would be looking to see, we would want to check if n divides the subtraction of these two things, right? So let's just use the plus for the sake of having a plus here. So we have this one minus this one. So we'd have to check that. Well, we know that a plus c minus b plus c is equal to a minus b. But we already know that n divides a minus b. That was the definition of how we set up the congruence in the first place. So this is going to be true, right? So we know that for a fact that this has to be true. We can check it algebraically as well, and everything kind of checks out. So yes, this is true. Okay, that's our definition, right? So we've already assumed that. So everything should check out, everything should be A-okay. So I think that's what Drizzy is trying to say. It's really not that hard to actually check this algebraically, provided you're comfortable starting with that definition and expanding on that definition. All right, so let's get into talking a little bit about multiplication. Now, like we did in your linear algebra class, we typically talk about multiplication separately from division because when you start working in different, when you start working with objects that are different than just regular numbers, division takes on a little bit of a different meaning, right? So when we were working with matrices, we really didn't have matrix division. It really turned into matrix inversion, or finding the inverse of a matrix in order to undo a multiplication. And the same thing's going to happen here. These are kind of very particular objects that we're working with, so we have to be a little more careful with how we talk about division. We're not really going to talk about division. We're really going to talk about, we want to understand one, we want to understand multiplication, and then two, we want to be able to try to undo multiplication. In other words, we're going to try to find inverses of objects to undo a multiplication. Integers. So, what? Integers. Sorry, what's division? Seems like an open problem. So just summarizing what we talked about there, and I need to spell right. I cannot spell right. So we're going to work on multiplication now. We're going to consider division separately. And the idea there is we're going to think about, it's not really going to be called division. We're going to be thinking about it as undoing multiplication. So we're going to be finding inverses when we get to that section of the course. So let's look at a leading example here. So let's take 20 mod 6. So if I think about 20 mod 6, we should be able to get up to 18, which leaves us with a remainder of 2. So 20 should be congruent to 2 mod 6. Now, what happens if we divide by 4? Just for funsies. Oh, interesting. Let's not make this 2. Let's make this 8. So I can add 6 to this. And it should be fine, right? So 20 should still be congruent to 8 mod 6. I guess this example was kind of showing my students what could go wrong when we try to divide recklessly. Right, so the idea here is, can we just blindly divide by 4 and do we end up getting a new relationship that will work? So if we divide both of these sides by 4, what do we actually get? We would get something like 5 congruent to 2 mod 6. Is that true? I don't think that's true. And that's not true. If we look at the difference between 5 and 2, we have 3. And 6 doesn't divide 3. So there's a problem there. So the idea here is, like division's just not going to work out the way that we want it to. And we have to have a little bit more care when we think about working with division. So division is just, it's not going to work in a nice helpful way that we think it is. However, we can use multiplication to our advantage, and multiplication does have some very nice properties we can use. The first one. So suppose we have two congruence relationships, so we know that A is congruent to B mod n, maybe C is congruent to D mod n. Then what do you think happens if we multiply A and C together? So is it true that we can just put B times D here? Does that make sense? Well, let's take our two small examples from before. And again, just trying to see if we can create some small examples. Maybe we'll prove this one maybe in more detail in a second. But what did we have? We had like 7 was congruent to 2 mod 5. And we knew that 9 was congruent to 4 mod 5. Now, if we were to do some multiplication of our first two numbers, we'd have 7 times 9, which is 63, right? And if we tried to multiply our second two numbers, we'd have 2 times 4, which is 8. So what we're really asking ourselves is it true that 63, is this congruent to 8 mod 5? So do the properties of remainders still stay the same when I do this multiplication? Is that true? I think this is okay, right? Because 63 mod 5, the smallest we can get is 3, but I think that 8's okay as well, right? 8's just like one step higher on that ladder that I'm allowed to look at, right? Like 3 is down here. If I add 5, I get to 8, right? So I think 8 is one of the numbers that I'm allowed to pick. So in this particular example, it looks like it's okay. So we might think that maybe we could do something like this, right? So this is the thought. Maybe we can do this multiplication, and maybe this multiplication is going to be okay if I multiply just the remainders on the right-hand side. So this one, I think, maybe needs a little bit more motivation. So maybe let's take a look at a proof for this one. I think we can do division, though, if we divide the mod number. That's interesting. I mean, in the example I gave, we couldn't really do it because I don't know if you can really divide 6 by 4 nicely and get a mod. You'd have to maybe explain to me how you'd want to do that division. Maybe you're thinking about it in a different way than I am. I'd be curious, though. Feel free to throw your thoughts out into the chat. Okay, so let's take a look. So what do we have? We can assume that A is congruent to B mod
Come on,
n.
Jeffrey, you can do it. Pave the way, put your back into it. Tell us why, show us how. Look at where you came from, look at you now.
Hi, Jeff, welcome in. So that's our assumption. We know that A is congruent to B mod n, and we know that C is congruent to D mod n. Our goal is to show that A times C is congruent to B times D mod n. My guess is that it's probably going to be easiest to do this using linear combinations. So we could convert this maybe into a form that's a little bit easier to work with. So, I mean, by definition, we know that n needs to divide a minus b, and n is also going to need to divide c minus d. And we talked about how we can convert this into linear combination. So if I want to convert this into a linear combination, we might say something like a and b are connected by some multiple of n, right? That's kind of the idea. So maybe we could say like a is equal to b plus some multiple of n, and maybe we could say c is equal to d plus some multiple of n. I'm just going to call the multiples k and l. K and l here can effectively be any integer that we want. But notice what we have. We have, you know, some multiple of n here, some multiple of n here. I don't know, is it useful for us to move this stuff over to the other side? So what's our goal? We want to show that AC needs to be equal to BD plus some multiple of n, right? Yeah, yes, Hadras, yeah. Yes, some of the custom intros are quite good. I agree. I like Jeff's a lot. Jeff's is great. I put a lot of effort into these intros. Hey, Darth, how's it going? How's your Thursday? Done classes for the day? Give Darth a little shout out. Darth is a good friend of the channel, variety streamer over on his channel. Mostly gaming over there, right? What have you been doing? Like a Plants vs. Zombies. Been doing some Have a Nice Death. I've seen some Fever meme. And I think we have a big Gartic phone stream coming up here on the weekend as well. Oh, this is fun. Okay. So I think Jeff is pointing us in the right direction. Jeff is saying this means that a minus b is a multiple of n, and c minus d is also a multiple of n. So any combination of a minus b's times c minus d's must also be a multiple of n. So that's kind of cool. So we're going to do something weird like this. We're going to say something like this. A minus b. If I multiply that c times, and then I add to that c minus d, and I multiply that by b times. This is a kind of a little weird, like shady little trick, but I kind of like it. So this has to be a multiple of n, because it's a multiple of a minus b plus a multiple of c minus d, right? So like this is divisible by n. And this is also divisible by n. That's kind of crazy. That's kind of cool. Okay, so let's expand this out and see what we get. So if we expand this out, we have a times c minus b times c plus b times c minus b times d. And the BC's cancel, and we get AC minus BD. We get the determinant of a 2x2 matrix. Just kidding.
Huh?
Just checking to see what Drizzy is talking about. So we want to substitute for A and B. Yeah. I mean, if we wanted to be like super particular about this, you're right. We would take that A minus B, we'd substitute in Kn, right? We'd take our C minus D, you know, like we might do some more substitutions. But I want to kind of work intuitively here, right? Like if I know that A minus B and C minus D are multiples of n, then I know that this combination of things should also be a multiple of n, right? And that's really what we need. We really need that this subtraction is some kind of multiple of n, right? And as soon as I have that, then we're pretty much good. Is this one obvious? Does this one feel obvious? So this one kind of feels obvious to me, right? Like, let's say we start with something that makes sense. Like, let's say I start with like 5 objects, and we're gonna be working with division by grouping by 3 or something like that, right? So let's say we're in a grouping by 3 environment. So we know that 5 and 2 look the same after I regroup by 3. Now, if I were to multiply both sides by 2, so in other words, I do this. I'm just going to take the left side, I'm going to multiply it by 2. I'm going to take the right side, I'm going to multiply it by 2. And I go through this regrouping by 3. Yeah, it kind of makes sense that this congruence should be true. It totally makes sense, right? Because all we're doing is just adding multiple copies of both sides. I can clearly see here that by adding the same number of multiples to both sides, I get the same relationship after grouping by 3. And even if you want, you could still group again by 3 here to get a 1, and I can still get, right? So it kind of intuitively makes sense when if I were to just kind of take this picture that I have and create C copies of it. It feels like it should work. I don't really see any issues here. This is not one that I don't really feel like proving, because this one feels a little bit more intuitive to me than property number 1. So I am super okay with property number 2. And maybe I'll just write down what we have here. So we started with 5 congruent to 2 mod 3. And we showed that if we multiply both sides by 2, so the updated picture is 10, is congruent to 4 mod 3, right? What we did was as we transitioned from the first one to the second one, we just made 2 copies of each picture. Yeah, Drizzy, I like it, right? Like each remainder also gets scaled by that same factor. So for me, the picture makes sense. I like the picture a lot. You know, we're going back to grade 2 and like working with base 10 blocks, right? It's a good time. Okay, so I have a couple examples here. A lot of what we might want to do with regard to working with modular arithmetic is just understanding best ways to simplify things. So if I have a string of things that are multiplied together, like this, we know that we can effectively look at each one of these pieces individually now and think about them mod 17, right? So I should be able to take 23, for example. I should be able to reduce that. How many things are left after I do that? Is it 6? So 23 can get reduced down to 6. What about 37? That'll go to 20 and then to 3. Is that 3? 17 doesn't divide 42. The closest I can get is 34, right? So 34, so 6, so 8. Please double check my remainders. And then 19 divided by 17 would give me a 2 remainder. So I think we should initially be able to do something like this. 6, 3, 8, and 2. Fantastic. And yeah, Drizzy's given us kind of a way to move forward. So now what I can do is now that I have smaller numbers to work with, I can now multiply these numbers and maybe go 6 times 3 is 18, 8 times 2 is 16, and then I can repeat this procedure over again. So I know, for example, 18 has a remainder of 1. And then finally, 1 times 16 is 16. So all of this reduces down to 16 modulo 17. Whoa, this one's fun. Okay, it doesn't look too bad. So this one's not too bad. I mean, the numbers aren't that big. In a typical number theory class, you might start to see numbers that are like quite large and be asked to do some simplification. Here it should be relatively straightforward to do some of the order of operations. So let's do 123 take away 54. Let's simplify that bracket. That gives us 69. And then we should be able to multiply. Do I want to multiply that by 5? Or do I want to keep it? I can probably just keep it as 69, right? Because I probably want to use the linearity here to help me out. So modular arithmetic, we've seen, can be broken up by addition, right? So I can really think about working mod 19 with that 132. So I'm just going to kind of rewrite this. I'm going to say, okay, well, let's just consider mod 19 over here. And let's consider mod 19 here. And then once we've done those pieces separately, we can just put the remainders back together and we'll be okay. So how does 132 work here? How many 19s? I'm not very familiar with... I'm not as familiar with my 19s times table as I am with my 17 times tables. I mean, there's not a lot here. I can just be a complete gooner about it and just like literally just do this until I get to 18. So 132 is 18 mod 19. And then here, I'm really just going to focus on the 67, right? We know that we should be able to simplify.
Excuse me, princess.
67 is taking over? What? Oh no, oh no. Oh,
Gonna get sticky.
Oh, too many, too many. You can't, I don't know. It was always 17 with me, but I don't know how 67 kind of got snuck in here. How many 19s go in there? 3. So 67, and I take away 3 copies of 19. What's left over? 10. So this will be 5 times 10 mod 19. I'm going to have to update my notes before the incoming group of students gets here. Okay, so we have an 18 mod 19, and then we have a 50. That should be probably 2, right? Like if I go 50 and I take away 2 copies of 19, that should probably work. So I'll get 12 here. Okay, and then the linearity allows me to combine these remainders back together and then do some final regrouping if I want to. So this would give us, what, 30 mod 19? All right, so 18 plus 12. And can I get 2? I can only get 1 in there, right? No, 2. Only 1. What's left over? 11? Is it 11? Why is division hard? Why is division so hard? Is it 69? Oh, did I write it down wrong? Oh no! Oh no! Our brains have been hijacked by the memes. Oh no. Yeah, it should be 69. It's not 67. Okay, let's do a little quick update to that. So if we go 69 mod 19. So 69, take away 19. I think we can probably take away 3 copies of 19. So that'll give us 12. Yeah, I guess it would be off by 2, right? Our remainder would be off by 2, so that makes sense. 5 times 12 is 60. All right, so we're looking at 60 mod 19. Is this also going to be off? Well, it's going to be off by 2, but 5 groups of 2, so off by 10, which still should be under 19. So let's see what that gets updated to. I think we should be able to do 2. 22, yeah, okay. So there's the 10 that I thought we would be out by. Okay, but I can take away another 19, and that would give me 20, 21, so it would give me 3. Okay, so we're really looking at 18 plus 3, which is 21. And that would give us 2 mod 19. How do we do? Did we eventually get there? It took us a while, but we got there, chat. We got there. through the 6 7s and 6 9s, we eventually got there. Honestly, I'd rather the kids laugh at 6 7 than 6 9. I guess so. I guess so. Okay, I feel good with that updated answer. So that gives you a little indication on how we might use multiplication to do some simplification, how we might use addition properties as well to do some simplification. So last thing I want to talk about before we take a little bit of a break here and move into the inverse section and the congruence class section is we just want to do a brief chat about exponentiation. We'll develop some strategies for simplifying powers as well, because I think that was something that Jeff mentioned, and I think it's something that's helpful to know how to do. So let's take a look at what that looks like. So a lot of these properties we're going to see are just extensions of properties we've seen already. So for example, if A is congruent to B mod n, whoops, that's all I need. Then I know, wait a second, is that true? This one I might need to prove. I thought this was an extension of the multiplication properties, but I'm not sure it's as obvious as I thought it was. So if A is congruent to B mod n, my property says that A to the m is congruent to B to the m mod n. In other words, I can take a power of both sides and this should be true. Is that true? That seems wild. Follows from the multiplication property and induction. Induction on M? Oh, I see what you're saying. Okay, here is the justification. I had to read my notes, but yeah, it makes sense now. So we think about A congruent to B mod n, and the multiplication property would allow us to take what we already know, which is A congruent to B mod n, and just like use it again to do a multiplication. So I can just take this expression that I know is true, multiply it by itself, and I get a times a is congruent to b times b mod n. And I just keep doing that as many times as I need in order to prove this property. So I think that's what we would effectively use induction here to make sure that this works up to m. But for the sake of just kind of understanding the intuition behind why this works, you just kind of repeat this process. So you'll eventually get a times a m times. All of that's going to be congruent to b times b m times mod n. So just rinse and repeat, and now we have a brand new property. That's kind of fun. I like that. Okay, so how would we approach simplifying something like this? We'll take a look at a small example, maybe start moving into some larger exponents. How I think about these is I try to kind of bust up the exponent into something that's maybe a little bit easier for us to work with, mod 7. So I might think about this as like 6 squared. Right, so I can kind of like move these 6's around in a way that might make sense. So in this case, I'm going to maybe group a couple of them together to get 36. Now, I guess I don't need brackets here. And I know, kind of based on some of the examples we've seen earlier, that we can really just kind of look at each of these 36's. We have 8 of them, and I can take each one of those 36's mod 7. So what do we get when we do division by 7 here? 35 is the highest we can get to, so we'll have a remainder of 1. Oh, that's kind of nice. So basically we get a remainder of 1, we have a power of 8. And then 1 to the 8 is now easy to simplify, so we just get 1 mod 7. Okay, so the idea here is, if you have a base and a really annoying power, maybe you can kind of group together a couple of those things to kind of help you simplify bits and pieces. Maybe if we got lucky in this case, we got a remainder of 1. Maybe you'll get a remainder of 0 or 1, and then it starts to kind of help a lot. It looks like this next one is not going to be a remainder of 1 or 0. So let's try this one. Let's look at 64 to the 72 mod 10. Okay, so basically just looking for the last digit after division by 10, right? Looking for the last digit. Oh, zone, got you. Okay, yeah. Yeah, so yeah, you're right. So we can always factor that. Got you. Okay, you're just saying that this is a difference of m's, I don't know how to call it, but yeah, we should always be able to factor that as a minus b times something else. Yeah, I got you. So it's always a multiple of a minus b is what you're saying. Yeah. Drizzy, yeah, I agree with you. Usually the canonical representatives, which we'll see after we take our break, are 0 to n minus 1. Sometimes I have seen number theory textbooks use... they usually use an equal number of positive congruence classes as negative congruence classes, right? So they usually take like n over 2 and then or something silly and use all 0 ends up being the middle, and they take a certain number of positive ones and they take a certain number of negative ones, and that becomes the congruence classes that they typically use. Yeah, negative 1 is often quite useful, which is probably why they decide to do that. Okay, so how do we want to tackle something like this? My intuition says I probably want to work with the 64 first. So it doesn't matter whether or not I have 64 to the power of 72 or the remainder of that, mod 10 to the power of 72. So let's just reduce that to 4. it's going to have the same remainder. So we're going to do 64 mod 10, which is 4. And then I'm going to maybe start thinking about grouping some of these 4s together to do a little bit of work. So in my notes here, I took 72 and I broke 72. Maybe I'll just make a little note here. So this note here is 64 is congruent to 4 mod 10. So that was my step number 1. And now I'm just going to do some regrouping. So I'm going to think about, okay, 72 can be broken up into 24 times 3. You could choose some other base. I just happen to know what 4 to the power of 3 is. I know 4 to the power of 3 is 64. So that just allows me to kind of repeat this process a couple of times. Right, so all I'm doing moving from here to here is saying, well, 72 is really just 3 times 24. I already know what 64 mod 10 is. It's 4. So I can kind of keep repeating this process to remove all of the powers of 3 from, all of the multiples of 3 from 72. So this, again, will get me down to 4 to the 24 mod 10. And I'll just do this one more time. I guess I can say 4 to the 3. That's going to be by 8, right? 8 times 3 is 24. So we know that's 64, so let's just go ahead and write 4 to the 8. So we basically have reduced the problem now down to 4 to the power of 8. Have we reduced it far enough that we can put it into a calculator and observe what the last digit is? I hope so. Okay, 4 to the power of 8, 65,536. If we do division by 10, that's going to leave us with that last digit, which is a remainder of 6. So this is 65,536 mod 10. And then when we do that division, we should end up with 6.